When you hear blockchain, I bet your mind jumps straight to Bitcoin, right? Cryptocurrency.
Oh, absolutely. That's the most common connection people make.
And yeah, crypto's huge, but the actual technology, it's got legs for so much more. And look, you're here because you want to grasp these big ideas, get right to the heart of it without wading through jargon forever.
Exactly. So today, we're really digging into blockchain fundamentals. We're going to unpack how it works, explore the really fascinating ways these networks agree on things, and tackle that big challenge, scalability.
Yeah, making it fast enough for, well, everything.
Right. We've sifted through quite a bit of material concepts, research plans to pull out the stuff that really matters, the interesting bits for you.
Our mission, if you will, is to give you a really clear and hopefully engaging picture of how this tech functions, the different flavors of agreement or consensus, and the ongoing push to make it scale.
So let's dive in.
Okay, let's start super basic. What is a blockchain, really?
Okay, so fundamentally, it's a distributed ledger. Think of it like a digital notebook, right?
Uh-huh.
But instead of one person holding it, or it being stored in one central database.
It's shared.
Exactly. It's shared and maintained by a whole network of computers. Nodes, they're usually called. Each node has a full copy, and they all follow strict rules to make sure new entries are legit.
Okay, distributed, spread out. Makes sense for avoiding central control, like with digital money.
Uh-huh.
But how do new entries, say, transactions, get added securely? And what's this about hashes I keep hearing?
Ah, right, hashes. That's where cryptographic hashing is key. It's basically clever math creating these unique digital fingerprints.
Fingerprint.
Yeah, digital ones. Super hard to fake or reverse engineer. So every block, which is just a group of transactions,
Okay.
gets its own unique hash, its fingerprint. But here's the really clever bit. Each new block also contains the fingerprint, the hash, of the block that came right before it.
So they're linked, like a chain.
Precisely. It creates this chain, linking them chronologically and making it tamper-proof. Imagine like Lego bricks.
Okay, I like Legos.
Each brick has its own unique mark, the hash, right? And it locks onto the mark of the brick before it. If you try to mess with the brick way back in the stack.
Its mark changes.
Exactly. And because all the next bricks are locked onto that original mark, the whole structure shows it's been tampered with. It's broken. That digital link makes the record basically immutable, unchangeable, and keeps everything in order.
That Lego analogy really helps, actually.
Mhm.
So transactions get bundled into these digital bricks, these blocks.
Mhm.
Then what? Who actually makes the new blocks?
Good question. That job falls to participants we usually call miners or validators. It depends on the specific system, the consensus method, which we'll definitely get into.
Yeah.
But in a system like Bitcoin, which uses proof of work, miners are basically competing.
Competing how? Like a race.
Sort of. They're racing to solve a really difficult computational puzzle.
Okay, computational puzzle. What does that actually mean? What are they doing?
Well, they're essentially trying to find a specific number called a nonce.
A nonce?
Yeah. It's like, imagine trying millions and millions of random numbers until you find one that when you mix it using a special function, a hash function, with all the recent transactions,
Sorry.
it spits out a result, a hash, that meets a certain criteria. Like maybe it has to start with a whole bunch of zeros. That's the target threshold.
So it's like a digital lottery, but based on computing power.
Kind of, yeah. It's designed to be hard, to take a lot of processing power, a lot of energy. The first miner to find that lucky nonce gets to propose the next block of transactions to everyone else.
And why bother? What's in it for them doing all that digital heavy lifting?
Ah, the reward. They get rewarded with brand new cryptocurrency. That's the block reward, and usually also the transaction fees people paid to get their transactions included in that block. It's the incentive to keep the network secure.
Right, makes sense. So they find the nonce, get the reward. What then? How does the rest of the network, all those other computers, know this new block is okay to add?
Great point. Once a miner proposes a block, all the other nodes on the network jump in to verify it.
Check their work, basically.
Pretty much. They check the digital signatures on the transactions that they valid. They check that nobody's trying to spend the same money twice. That's the double spending problem.
Okay.
And they confirm the block's hash meets the difficulty target using the nonce the miner found. If the majority of the network gives it the thumbs up, says, yep, looks good,
Then it gets added.
then it gets added to the chain permanently. It becomes part of that immutable history. So it's this constant peer review by the network that maintains the trust and security.
Okay, got it. That whole process makes a lot more sense now. So you mentioned miners or validators, depending on the system, and these consensus mechanisms. What are those exactly, and why are there so many different kinds?
Right, consensus mechanisms. They are the core rule books, essentially, that let this whole decentralized network agree on one single version of history, one single truth about the transactions, without needing a central boss to say so.
Okay. Agreement without a dictator.
Exactly. And the fascinating thing is, there's no one-size-fits-all answer. Different blockchains use different methods, and each one has its own, pros and cons. They balance things like security, speed, and how decentralized they are differently.
Okay, so let's walk through some of them. Proof of work is the big one, right? Bitcoin's method.
That's the original, yeah.
Yeah.
Proof of work, or POW, like we discussed, miners solve that energy-intensive puzzle. Its huge strength is that it's battle-tested, it's been around for over a decade, very secure, very resistant to censorship.
Well, like the energy.
That's the big drawback, yeah. Very high energy consumption. And it's relatively slow, transaction-wise. Bitcoin, for example, handles maybe around 7 transactions per second.
Only 7.
Wow.
Yeah, in today's world, that feels like a limitation. So what else is there? Proof of stake is often mentioned as greener.
Proof of stake, or POS, yes. It was designed largely to be more energy efficient. Here, instead of mining, participants called validators stake their own crypto.
They lock it up.
Yeah, they lock up some of their coins as collateral, basically. This gives them a chance to be chosen to propose or validate new blocks. Often, the more you stake, the higher your chance.
Makes sense. Benefits.
Big one is much lower energy use. Huge difference. And potentially faster speeds, higher transaction throughput.
Downsides.
Well, there are debates. One classic issue was the nothing at stake problem, like why wouldn't a validator approve multiple chains if it costs them nothing? Though modern systems have ways to punish bad behavior called slashing.
Okay.
There's also concern about stake centralization. If a few players hold most of the staked coins, could they gain too much control? It's an ongoing discussion, that potential centralization versus the promise of decentralization.
Right, because if a few hold all the cards or coins, they have more sway.
Yeah.
What about delegated proof of stake, DPoS? How's that different?
DPoS takes the staking idea and adds a layer of, well, delegation. Token holders vote for a smaller set of delegates or block producers.
Like electing representatives.
Kind of, yeah. These elected delegates then run the consensus process for everyone else. The upside. Often very fast blocks, really high throughput, maybe hundreds, even thousands of transactions per second in some cases.
Wow, that's a leap.
It is, but the trade-off is usually more centralization, right? Power is in the hands of that smaller elected group. And there can be governance issues, vote buying, delegates maybe acting in their own interest.
Okay, so again, that speed versus decentralization trade-off pops up. What about proof of authority? Sounds official.
Yeah, proof of authority, POA. It's often used in more controlled settings like private or consortium blockchains. Here, a limited number of pre-approved entities act as validators.
So you know who they are.
Exactly. Their identities are known, which adds accountability. POA chains can be very fast and predictable, but clearly it's more centralized. You're trusting those specific authorities, and it's less resistant to censorship than, say, POW.
Got it. So different tools for different jobs. I saw some more exotic names too. Proof of space, proof of burn.
Huh, yeah, the names get creative. Proof of space, or proof of capacity, uses hard drive space. Validators dedicate disk storage to solving challenges. The idea is it uses less energy than POW's processing power, and disk space is pretty common hardware.
Okay, and proof of burn sounds destructive.
It kind of is. Validators literally burn, permanently destroy some coins to prove commitment. By sacrificing tokens, they earn the right to mine or validate, often based on how much they burned.
Huh.
Why? It's energy efficient, no ongoing resource drain like POW. But yeah, you're destroying value, reducing the token supply. Some see it as wasteful. It's like saying, I'm serious, look, I'm burning my own money.
Interesting psychological angle almost. What about proof of history? That sounds like it relates to time.
You got it. Proof of history. POW Solana is famous for using this. It's a really clever way to create a verifiable timestamp, a record of time passing, using sequential hashes.
The clock for the blockchain.
Essentially, yeah. It lets the network agree on the order of events super quickly without constant back and forth chatter. This allows for incredibly fast blocks, potentially rivaling traditional payment systems. The caveat is it relies on some newer cryptographic ideas, so its long-term characteristics are still under scrutiny.
Okay, cutting edge stuff. Then there was proof of elapsed time and proof of activity.
Right. Proof of elapsed time, POET, uses special, secure hardware, think Intel SGX chips, to randomly assign wait times. Whoever gets the shortest wait time wins the chance to make the next block. It aims for fairness and low energy use, but
Depends on trusting the hardware.
exactly. You're reliant on that specific hardware and its manufacturer. Proof of activity is a hybrid, mixing POW and POS. Miners do some initial light work, then stakers finalize the block. Tries to get the best of both worlds security-wise, but it can be pretty complex.
And one more, proof of reputation, like a credit score for validators.
That's a good analogy. Validators build up reputation over time by being reliable. Their reputation score influences their chances of creating blocks. It encourages good long-term behavior, but
Right.
could be gamed, right? Validators could collude to boost each other's rep. And defining and maintaining reputation fairly in a decentralized way is tricky.
Wow. Okay, that is a lot of different ways to get everyone on the same page. It really hammers home that point. No single perfect answer, just different trade-offs.
Yeah,
Security, decentralization, speed.
precisely. Which leads us neatly into that huge challenge, scalability. We keep hearing about chains getting clogged, struggling with transaction volume. Why is that such a fundamental problem?
Yeah, what's the bottleneck?
It often boils down to something called the scalability trilemma.
Trilemma. Okay, three things fighting each other.
You got it. The idea is it's inherently really hard to maximize three crucial things at the same time. Decentralization, security, and scalability, which means speed and transaction capacity. Usually, if you crank up two of them, the third one takes a hit.
So if you want it super fast, super scalable.
You might have to sacrifice some decentralization, maybe make it harder for average users to run a full node, concentrating power, or maybe compromise slightly on certain security aspects, though that's generally avoided.
Okay, so how are people trying to solve this trilemma,
Mm-hmm.
or at least manage it?
Yeah,
I hear about layer 1, layer 2 solutions. Sharding.
right. Broadly, there are two main approaches. Layer 1 solutions change the base blockchain itself. Sharding is a big one here.
Sharding, like splitting it up.
Exactly. You partition the blockchain into multiple smaller chains or shards. Each shard processes its own transactions in parallel. Think going from one congested highway lane to many lanes. It dramatically increases capacity. Ethereum's big upgrade plan heavily involves sharding.
If that makes sense conceptually.
Other layer 1 tweaks might be just increasing the block size, like Bitcoin Cash did, or making blocks faster. But those often have trade-offs, maybe pushing towards centralization or increasing the risk of orphan blocks, valid blocks that get left behind.
All right, the trade-offs again. So if that's layer 1, changing the base, what's layer 2?
Layer 2 solutions are built on top of the main blockchain, Layer 1. They handle most of the transaction load off-chain, only using the main chain for final settlement or disputes.
Like an express lane that merges back later.
That's a great analogy. State channels, like Bitcoin's Lightning Network, are an example. Two people can open a private channel, do tons of transactions back and forth almost instantly with tiny fees, and only record the final net result on the main Bitcoin blockchain when they close the channel.
Okay, that sounds efficient for payments.
Very. Another huge Layer 2 category is rollups. These bundle or roll up hundreds or thousands of transactions off-chain, process them, and then post just a compressed summary and a cryptographic proof back to Layer 1.
So layer 1 just sees the summary, not every single transaction.
Exactly. It dramatically reduces the load on Layer 1, boosting throughput massively. There are different kinds, like optimistic rollups and ZK rollups, using different proof methods, but the core idea is similar. Do the heavy lifting off-chain, settle concisely on-chain.
Got it. Layer 1 is the foundation. Layer 2 adds speedways on top. What about totally different structures? I think I said something about DAGs, directed acyclic graphs.
Yeah, DAGs.
Yeah.
That's moving away from the linear chain of blocks altogether. In a DAG, transactions can confirm multiple previous transactions directly, creating this more complex web-like structure.
Not just one block after another.
Right. The potential upside is high parallelism transactions can be confirmed simultaneously, potentially leading to very high throughput without the block bottleneck. Projects like IOTA or Hedera Hashgraph use DAG-like structures. It's a different approach to the whole ledger idea, and research continues into other non-linear structures too.
Okay, this has been, wow, a really thorough journey. I think the big takeaway for me, and hopefully for you listening, is that blockchain is way more than just crypto. It's this foundational tech, super versatile, but how it works under the hood, well, it varies a lot.
Absolutely. Proof of work was a starting point, but the innovation and consensus is just nonstop. POS, POH, all the others, each is a different attempt to balance those core priorities.
And that scalability trilemma, that constant tension between keeping it decentralized, secure, and fast enough That's clearly what's pushing all this innovation, right?
Yeah.
Layer 1 changes, layer 2 solutions, even rethinking the whole chain structure with DAX.
It really is the central challenge driving so much research and development, which leads to maybe a final thought for you to chew on.
Okay.
Given this incredibly rapid evolution, what do you think the next big leap will be? Will we see a consensus mechanism that somehow squares the circle, a layer 2 solution that becomes totally seamless? Or maybe something completely unexpected emerges? Think about how these different technical choices, energy use, governance, speed, could really shape how we end up using decentralized systems in, well, pretty much every field imaginable.